Hello guys, welcome back to MG School of Mining and Geology YouTube channel. In today's session, we're dealing with the P-T-t path in metamorphic petrology. We're basically trying to understand the process of burial, heating, and exhumation of rocks. We are trying to understand the clockwise path and anti-clockwise path, looking strictly into the prograde and retrograde metamorphism. Please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. So basically, a P-T-t path shows how a rock changes its pressure, temperature, and time, all right, with the time. So it records the rock's life journey during burial, heating, and exhumation, or during the rocks being closer to the surface of the earth. Okay, so I want you to think of this as a story of a rock inside the earth. That's what you call the P-T-t path. All right. So we've got different paths in metamorphism. We've got the prograde metamorphism and retrograde metamorphism. Prograde, it's when you are increasing the conditions, and the retrograde, that's when you are lowering the conditions. That is to say, prograde, you're increasing the temperatures, retrograde, you are cooling. So prograde, you're heating, retrograde, you are cooling. So we've got the clockwise and anti-clockwise path. This one is the normal clockwise path. All right, this one is the normal clockwise path, wherein the rocks or the sediments are undergoing burial. All right, and wherein the pressure starts to increase first, and the pressure starts to increase first, and then with the time, all right, with the time, those rocks, they start to experience a constant or to experience heating. All right, experience heating, that's this part, and then after that, due to uplifting or due to erosion and or because of the effect of buoyancy, we will have a cooling and decompression. That is what you call a retrograde. But when you're increasing the pressures and temperatures, that is the prograde. So this is the clockwise path. So the rate of prograde metamorphism and the rate of retrograde metamorphism may not be the same. So you find that we have the pressure first. All right, we have got the heating, then after that you'd be having cooling. For example, the duration of the path from start or to finish will vary from rock to rock depending on the tectonic history. So let's find these, let's describe these paths, all right? So when we're looking here, we're looking at the pressure temperature, that these, they do not rise together. They are not rising together or simultaneously. So you find that we have rising pressure first, then followed by rising temperature. So in textbook, we often talk about metamorphic rate as if pressure and temperature go up in unison. No, they do not rise together. But in reality, pressure rises quickly first, okay, as soon as the rocks, they get to be buried. All right, the pressure rises, but the temperature, because we know that the rocks are poor conductors of heat, so we know the temperature, it will take time for that for those rocks to, you know, have an increase in temperature. All right, this is the same way you can imagine you putting a potato or sweet potato inside your pot, all right, or inside the boiling water. So the pressure will increase first, but obviously the heat, it won't be enough, which is why you don't expect 2 minutes after you put your sweet potato, inside the boiling water to be, you know, ready to be eaten, all right, within this a short period of time. But with the time, when the temperatures start to increase, then that's when you expect the sweet potato to be ready to be eaten. So later on, as the pressure rises first, temperature would be lagging behind, all right? So this is why we start to have highest pressure and then followed by the highest temperature. And we've mentioned that these things, they do not happen at the same time, so they happen at different times. The other one happens first, or first, then the other one lags behind. So in most clockwise paths, especially in mountain building events or in mountain belts, where two things they get to collide, all right, we expect the pressure to come first, right? Because when what we expect during the mountain building event is the fact that we'll be having crustal thickening. So the rocks here, they will be deeply buried. Deeply buried. So when the rock is the deepest, so during mountain building event, we are having an increase in pressure. We're having increase in pressure. All right, then these rocks will be deeply buried. So the temperature comes later, after the rock has already started exhuming, because the heat transfer is low. The rocks are poor conductors of heat. So the real metamorphic rate, okay, what we see in minerals is recorded at Tmax. So it means the Pmax is not that important. What is important is the Tmax, because temperature is the one that allows the minerals to grow. All right, it's the one that allows the minerals to grow. All right, but not this pressure. Okay. So which is why the maximum temperature conditions are the ones that allows the minerals to grow, and those minerals are going to be locked inside the equilibrium assemblage. So another thing that we should take into consideration is the variations in the retrograde paths. So normally the prograde transition happen when rocks are buried. So immediately when we bury the rocks, the prograde transition happens. But sometimes a retrograde path across mineral boundaries. For example, kyanite to sillimanite transition. All right. Sometimes, we once dealt with this. All right. So sometimes usually, for example, from kyanite to sillimanite transition, all right? Usually, this is a prograde, more heat, but at the same depth or constant depth, right? But in path A2, which I'll show you where path A2 is, the rock crosses this boundary while cooling. So you'd find that you are crossing this boundary, and then after that, cooling takes place, because this will be the graph, this will be temperature, this will be pressure, and then this one will be depth. Okay, so this one will be crossing, this will be crossing this transition, and at the same time will be cooling. All right, this will be path A2, because as we're going that way, the temperature is decreasing. Okay, so it means now, because transition is taking place while cooling during retrograde, it means now we're going to be resulting in only amount of, because remember this one, it happens when you are having, this one happens when we are having retrograde. It means now we'll find that if this is a kyanite, you'll find the sillimanite replacing this thing like this. All right, you'll find sillimanite replacing here the rims. Then this will be the sillimanite, and then the core will be the kyanite. All right, the core will be the kyanite. So that's why we're saying only small amounts of sillimanite may replace kyanite, because the retrograde reactions are sluggish and need fluids. Remember, most of the fluid was lost during prograde metamorphism. So now, during retrograde, we don't have sufficient fluids that would allow the reaction to take place. All right, which is why reaction is not that intense. During a retrograde. All right, during retrograde. So I hope it makes sense. Another thing that we must understand is the metamorphic P-T-t path may be addressed by three things, may be addressed by three things. Observation of overprints, okay, by observation of overprints. So this would give relative sequence of metamorphism and by what you call a geothermal barometry, okay, of zoned minerals, which will give the quantitative pressure temperature points along the path, and what you call the pseudosections, so which would integrate mineral chemistry and bulk composition to constrain the pressure temperature path more precisely and holistically. So, but this will deal with them in greater detail in just a few. All right. So the first one, the observations, observing partial overprints of one mineral assemblage upon another. So we understand that in metamorphic rocks, older minerals may survive, all right, and then they become relics, okay, when a new metamorphic event occurs. So this helps in this way that the relic mineral preserve the pressure temperature conditions of an earlier stage, all right, prograde or retrograde metamorphism. All right, these old minerals, they will contain they would have information about the pressure temperatures of the early events. So, for example, kyanite cores, all right, kyanite cores. Remember, I've already mentioned the fact that the kyanite, because of during retrograde, all right, the kyanite will be the core, and then along the rim will be having the sillimanite, because we did not have sufficient amount of heat. And remember, for reaction to take place, we need sufficient amount of heat. We need heat and we need fluid. So we need heat and we need fluid. But because most of the fluid would have been lost during the prograde metamorphism, then during retrograde we don't have sufficient amount of heat and also the sufficient amount of fluids. All right. So one thing that's why during retrograde we do not have sufficient heat that we want, and we don't have sufficient fluid that we want. All right. So now we end up sillimanite not replacing the entire kyanite, but now it only replaces some of the kyanite along the rims. Right. So that's why we're saying kyanite cores inside sillimanite rims can tell you that the rock first reached the kyanite stable conditions. So it will tell us that the rock was reaching the stable kyanite conditions, that is to say prograde, because you kyanite develops during prograde metamorphism when the temperatures are rising, right? Before partially retrograding to sillimanite. Now we don't have sufficient amount of heat and fluid because some of the fluids were lost during prograde. Then because of that, all right, we start to have new conditions now, that is to say cooling, that would bring us this what you call a sillimanite. So observing overprints allows you to trace the sequence of mineral formation, helping reconstruct a segment of the P-T-t path. All right. And then you apply also the conventional geothermometers and geobarometers. All right. That is to say what you call a geothermal barometry. Okay. So many metamorphic minerals are chemically zoned, meaning their composition changes from the core to the rims. All right. So that's one thing that I want to bring to attention. So you know that for example, even pressure case can show this. So you know we would be having cores, all right, and then something like that. We know here the rims would be having would have formed at low temperatures, and then this one would have formed at high temperatures. All right. So so this one will be usually containing Metamorphic components, and the cores and the rims will be containing the felsic components. Okay. So how it helps, the core composition reflects the early pressure temperature conditions because we formed these ones first, while the rim composition reflects the later pressure temperature conditions. So by applying calibrated thermometers, okay, and barometers to these zones, we're applying these calibrated thermometers and barometers to these zones, that is to say the cores and the rims, all right? We will be able to quantitatively reconstruct the pressure temperature evolution during the mineral growth, though, so that this would allow you to track a continuous pressure temperature path, not just a single point. And last but not least, metamorphic path may be addressed by using quantitative phase diagrams, that is to say what you call pseudosections, all right, where in pseudosections are calculated phase diagrams for a rock or of a known bulk composition. So they show which mineral assemblages are stable at different pressure temperature conditions. So this would help by comparing observed mineral assemblages and composition to predict assemblages in the pseudosection. You can map the pressure temperature conditions in different stages. It is particularly powerful to for complex metamorphic rocks where multiple reactions overlap, and it integrates mineral chemistry and bulk composition. So basically we are combining mineral chemistry and bulk composition, all right, to be able to unravel the complex metamorphic history. So this method can refine or confirm the path inferred from cores, or from cores, rims, or from overprints. That is to say, you are confirming what you remember. Number one were those overprints, and then number two, we're using the rims and cores. So these quantitative phase diagrams, you'll be able to confirm 1 and 2. So retrograde reactions, or what you call on the cooling or exhumation path, are usually incomplete, and we want to understand why. So the main reason is the fact that when rocks are cooling, basically the rocks during retrograde, they cool because of the effect of the uplifting, right? So or erosion. So we know during erosion, these rocks would would come closer to the surface of the earth, or during uplifting, right? So when rocks are cooling and coming back to the surface, they do not have enough energy for big mineral changes. So reactions, we know, I've already mentioned that they need heat and fluids to allow atoms to move and reorganize. But on the retrograde path, the rock is cooling, all right? Unless heat, atoms are sluggish. So also fluids would have escaped during prograde reactions, as I've explained. So without fluids, reactions cannot easily take place. So what happens now? So instead of fully transforming, you get only minor replacement, like for example, wherein you saw wherein a sillimanite were replacing a small portion of the carnite. So it's because of retrograde reactions, the reactions that were taking place during cooling, all right, during cooling, wherein we do not have sufficient amount of heat and sufficient amount of fluids that would be necessary for the reaction to take place, all right. So how do rocks return to the surface of the earth? By erosion, as I've already mentioned, by erosion, tectonic uplifting, by buoyancy, and of course by extinction. Okay, so for example, I mean, let me give you this example. We know that the rocks would be on top of one another, right? The pressure is going down like that, right? The pressure is going down like that. But if we erode, all right, we erode some of the overlying materials, so this would bounce back, all right? Then they would return to their original positions, all right? So they're going back to the surface. Right? That is the effect of erosion. And tectonic uplifting, so we know tectonic uplifting, what does it do? It makes sure that the rocks are brought closer to the surface of the earth. And of course, the buoyancy and the expansion. Okay. Sorry, yeah. So as I've mentioned that, I will also explain the transition from kyanite to sillimanite along path A2. that where retrograde was taking place. All right, so promise that we will do that. But now I want to bring to your attention, I want you to be familiar with this diagram. So you see you have got the pressure on your left hand side, and on your y-axis, and you've got temperature on your x-axis, and also the depth. And you've got two paths. You've got the one that goes from A to Pmax, and here when it gets here, remember we're still within the Carnot stability zone. And then when we get here, when we transition to basically we're still here. Yeah, we're still on the Carnot. So but we see two paths. We see Tmax and A2. So we see basically A2 and A1. So we see A1 and A2. All right. But on A2, we see this cooling. We see this cooling, for example, here. All right. Then on A1, it will extend from A1 and then now into Tmax and then into B. So into B. So you will be able, for example, in the test, usually they would like you to interpret this. They can give you this and then they tell you to explain what is really going on here. All right. So I want you to familiarize yourself with this picture. But I'll come back to this picture in a few. All right, so in stage A, to Pmax, burial and pressure building. So rock is buried deeper, pressure increases faster than the temperature. We've already mentioned the fact that the Pmax, or we've got maximum pressure first, then because the rocks are poor conductor, or because the rocks are poor conductors of heat, then temperature would come later on. So mineral assemblages, we expect the minerals that are happening at low temperatures, that is to say the green minerals and the chloride, for example, epidotes, right? So Carnot is stable. Carnot is stable. So which is why here you see that we are in the Carnot zone. So here in this part, we are in the Carnot zone. The Carnot is stable because we are increasing the temperature progressively during what you call prograde metamorphism. So from A to B or to Pmax, it will be the prograde metamorphism. All right. So yes. So if you haven't yet visited our video on these polymorphs, kyanite, sillimanite, etc., and andalusite, please, you're more than welcome to visit MJ School of Mining and Geology to also learn about these things and the questions that you can expect thereof. So the analogy that I want to bring to your attention is, if you're going deeper into the gold, the cold mine, it's deep but still cool. All right, it is deep but it is still cool. So that's why. But the pressure, it's high, but the temperature is still cool. All right. So that's why I want you to imagine you going deeper into the cold mine. All right. Then now, the deepest burial the rock can experience, it what you call the Pmax. Still relatively cool for the depth. All right. So minerals, you are having that kyanite and the garnet and the garnet. All right, beginning to the garnet beginning to grow, and also the epidote. So during prograde, you are developing, you're growing this garnet. Right. So now, after deepest burial, rock heats up at high pressure because you are at the greater depth. All right, you're at the greater depth, and we know that the deeper you go, the hotter it becomes. Then it means that the temperature, all right, it progressively rises. All right, so minerals, for example, garnet, sterolite, muscovite, they would give you the reaction. They would give you things like sillimanite and K-phosphorus. All right. So transition into amphibolite fascies, and this T maximum is the hottest point you could ever reach. So the hottest rock will ever get. So the minerals will be that sillimanite and phosphorus and the garnet. So the partial melting may start if H2O is present, because we know the water lowers the melting temperatures so that the melting can take place. All right. So I'm just quickly taking you through this, but we'll go back to that diagram and now explain the diagram in greater details. Now, finally, from A1 to B, that is where cooling is taking place at shallow. The most important part is cooling at shallow depth. Then now it means the rocks were brought closer to the surface of the earth. So rocks reaches shallow crust or surface. So minerals were having green sheet fasces. All right, and then rocks are fully retrogressed, recording its journey. Right, so key takeaways about that is the Pmax is the deepest point or the highest pressure, and then Tmax is the hottest point at the highest temperature. Prograde path is wherein you're having burial and heating. We're having burial and heating, wherein you start with the burial first, wherein you'd have high pressures, and later on, because rocks are poor conductors of heat, then later on now you'd have Tmax. All right, that is the prograde path. But retrograde path is the opposite. If the prograde is going that way, retrograde, it will be going that way. All right, retrograde path, exhumation and cooling means you're bringing the rocks closer to the surface of the earth. And we've already explained that erosion, buoyancy, and the uplifting and many other factors that can cause this exhumation and cooling, bringing the rocks closer to the surface of the earth. So minerals change along the path and record the rock's journey. All right, and they record the rock's journey. All right, all right. All right, no, it's fine. I wanted this. Sorry about that. Okay, that's fine. I wanted to see where that is. Okay, so let's wrap this up. So you know that the clockwise path is the pressure that increases first, and then that is to say during a burial or crustal thickening, then the temperature rises slowly. Also, and we've mentioned the fact that this would be happening in mountain buildings, all right, events. And then we've got the anti-clockwise that will go that way. Anti-clockwise path, that will be the temperature increases early during magma intrusions while the pressure lags. So that is the opposite. Remember, this the clockwise path, we're having the pressure that increases first, then the temperature rises slowly, all right, during what you call the mountain building events, where we're having a crustal thickening, all right. So I want you to think of that. But now during retrograde, what do we expect? We expect the temperature now is the opposite now. The temperature must rise first. We must have Pmax first. Then here we must have Pmax. Then I want to bring to your attention that remember this is common during magmatic intrusion. All right, during magma intrusion. Then what do we know from magma intrusion? Magma brings us or brings heat. So that's why the temperature would increase first while the pressure is still lagging. All right. So this retrograde is common in the granulite, is common in the granulite fasces. It's common in the granulite fasces terrains, right? With magmatic heating. So this is common there. All right. So all that I wanted to bring to attention is understanding that the difference between the clockwise and anti-clockwise, and that during prograde path, that is to say the upward path, the rocks heat and get to be heated or get to be buried and heated. All right, and then you are forming new minerals. But during retrograde, the rocks is exhumed and cooled, wherein minerals may break down or re-equilibrate. So during retrograde, you are expecting the minerals to break down or to re-equilibrate. So, but sometimes the forward and the backward path, they look similar, but sometimes they are very different. But everything depends on the tectonic and tectonics and the fluids, right? That's one thing that I wanted to bring to your attention, right? But now let's go to that yes, this one. Let's explain this thing in greater detail. Let's explain this thing in greater detail, and I think then we can call it a day or a night or whatever, depending on what time you're watching this video. All right. So let's look closely into this diagram. I want you to familiarize yourself with this, all right? So we have got different paths. We have got path A, all right? We have got path A. We've got path A that is moving the, all right? And then we have got path B, and you have got path C. And path C, automatically, what do you see? You see retro, you see the retrograde. Then that is to say, you see this cooling. So let's start with A, all right? So with A, this A, you can tell without any fear of doubt that this is a clockwise. So you can tell that this is a clockwise path, all right? This is a clockwise path, all right? And we've already mentioned that this would be typical in orogenic belt, or if you don't want to say that, you can say regional metamorphism. If you don't want to say regional metamorphism, you can say during mountain building, or you can say mountain building. All right, that's where we're expecting that. So this is a prograde wherein we're having burial and heating. So I want you to understand what's really or what is happening. All right. So the first thing is the fact that the rocks are buried during crustal thickening when those two crust are colliding. We are having crustal thickening or this buckling up, for example. All right. So rocks are going to be buried. All right, the rocks are going to be buried. Let's imagine this is a rock. So this will be a buried. So this will be a buried rock. So if it wasn't because of this crustal thickening, this mountain building event, we wouldn't be having the rocks which are well buried. But now, because of this burial, what do we expect? We expect the pressure to increase much faster than the temperature at first. All right. Why is that happening that way? Because the pressure will always equilibrate instantly, but the heat moves slowly because the rocks are poor conductors of heat. But with the pressure equilibrate instantly. All right. So it means that the rock will always reach its P, or the maximum pressure. All right. It will reach the maximum pressure while still cooling. So it will reach the not cooling, but while it's still cool, it is still cool. So the rock will reach its maximum pressure while it is still cool. Like I said, you imagine you going deeper into the cold mine. Right, the pressure increases, but the temperature is still relatively cool. So it means now later on. All right. Later on, it could be because of different things. It could be the heat from what you call it, the radioactive decay. All right. So so it means you expect the thickened crust and magmatism to raise the temperature. You expect the thickened crust and magmatism to raise the temperature. All right. So it means now you'll be having the highest the temperature. But because of the effect of erosion and uplifting, which take place, now pressure would start to decrease, decompression. While heat is still arriving, you're still bringing in more heat. So that is to say, you'll be now having the negative slope path. You'll be having this negative slope path. Why? Because you are decreasing the temperature, you're decreasing the pressure. You can see the pressure is decreasing because this path is going a little bit down. You're decreasing the pressure, but when you're decreasing the pressure, and because of the effect of erosion, and or uplifting, the pressure will decrease, but the heat will still be arriving. All right. Now that would eventually make sure that this maximum temperature is reached. All right, this maximum temperature is reached. After that, you expect both pressure and temperature to decrease as the rocks moves back to the surface because of that erosion and whatever that brought the rock closer to the surface of Earth. That's why after that you expect the temperature is decreasing and also the pressure is decreasing. After that, that is the path A. So please, in the exam, you must be able to explain this path. So, but the minerals and fascists that we expect go path A. We expect the in the prograde. In the prograde, we expect the chloride. We expect the chloride. We expect the garnet. We expect the staurolite. We expect the kyanite. We expect the sillimanite, right? During prograde metamorphism. But during retrograde, because you are cooling, during retrograde, you must have guessed it right. We expect the chloride. We expect the muscovite. You can expect the sericite, all right? That is the idea that I want to bring to attention. So we've mentioned this clockwise path, wherein the pressure increases first, then followed by the temperature. All right, and we said this is typical of regional metamorphism or the orogenic events. Now, with path B now, in path B, here, path B. Here, that's where you are having what we call contact metamorphism. Here you are having contact metamorphism. You are having contact metamorphism. Why and how? I mean, you know that the rocks must be heated and cooled at almost constant pressure. You see that the pressure is constant. The pressure is constant here, right? So we are having the constant pressure, right? So it means we expect the rocks to be heated and then get to be cooled at the constant pressure. All right, as the temperature is decreasing, all right, as the temperature is decreasing, the pressure should be constant. That's the idea that I want to bring to your attention. But what really causes this? Okay, this because you know the temperature is decreasing, it means this would be caused by shallow level. This would be caused by shallow level magmatism. All right, this would be caused by shallow level magmatism, okay, or magmatic intrusions, or for example like granite or the basalt plutons at shallow depth. So it means now this would forces the rocks near the intrusions to be baked. And then if the rocks near the intrusions, if this is the intrusions, the rocks near these intrusions, they would be baked. Then now these rocks, their temperature would rise quickly. But of course, the pressure does not change much. We don't expect the pressure to, that's why this pressure is nearly constant, or it's constant, because the only thing that is taking place or that is having much effect, it will be the pressure. It will be the temperature, not the pressure. All right, not the pressure. That is the part B. So because of the intrusions, you know, you have the background of metamorphic, you know, rocks. You know, we expect the Hornfels fascist minerals, like for example, cordierite, the andalusite, selimanite, you know, but that would also depend on the temperatures, all right? So the key idea about the path B is you understanding the contact metamorphism, where, which brings the heat at shallow depth. All right, you can have the granite pluton or the basalt pluton that makes the temperature of the rocks near the intrusions to rise quickly while we're still having moderate to constant pressures. That's the idea that I want to bring to your attention. All right. And now that's why you are having this flat path. Now with the C, with the C, we've already mentioned the fact that with C we are having a retrograde, and then here we expect this thing to be taking place near what you call the more granulite terrains or mafic magma intrusions. We expect it the mafic magma intrusions. Mafic magma intrusions. We expect these inside the mafic magma intrusions or the granulite terrains. Okay, so we know that during intrusions, what are we bringing? We are bringing large volume of hot mafic magma. This large volume of hot mafic magma, which intrude the lowest crust or the shallow crust. All right. So now it means this intrusion would raises the pressure and temperature together. All right, this would raises the pressure and temperature together. All right, which is why this path slope upward. You find this path slope upward to the right. Okay, it's upward to the right because the pressure is increasing and also the temperature is increasing. That's why we see this path rising towards the right. So, but after this magmatism, rocks, what do you expect? Now, okay, at the same time now, the temperature rises because the rocks closer to that, they get to, you know, undergo baking, all right? Now, after magmatism, we'd expect these rocks to, but at a nearly constant pressure. It could be 0.7 maybe, all right, at nearly constant pressure. Why? Because the heavy mafic magma would not let the crust to float up easily. That won't happen, right? That won't happen. The mafic magma would not allow the crust to float up easily. Then that will give us the nearly constant pressure. All right, and that's why we expect the mineral fascists that we expect here. It will be the granite fascists, right? It will be the granulite fascists, right? So you know, the key idea is during anti-clockwise path, you raise the temperature first, all right, and then after that, it will be the pressure that is in the anti-clockwise, right? So that is the idea that I want to bring to your attention. All right. So basically, in the exam, like I said, you might be expected to explain this path and or just be able to understand this path of what's really happening. All right. So I think this will bring us to the end of our lesson. And we are really thankful for joining us today. And you know what I'm going to say. Please don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. And I know you already know what I'm about to say. I will always like to say, until next time, cheers.